in a triangle ABC, show that a square multiplied by cos square b minus cos square c, b square multiplied by cos square c minus cos square a, plus c square multiplied by cos square a minus cos square b equals to 0. Okay, we have to prove this equals to 0, and this question can be solved by using properties of triangle. The solution is quite easy, very simple. We just use simple idea to solve this question. It looks quite tough, but by using the properties of triangle, by using the sine rule and applying a basic algebra, we can easily prove equals to 0, that is RHS. So first of all, let us take LHS. Before proceeding, we will convert all cos theta in terms of sin theta, that is cos square b equals to 1 minus sin square b, and cos square c can be written as 1 minus sin square c, and cos square b can be written as 1 minus sin square b, and so on, all other terms. So we get a square in place of cos square b, 1 minus sin square b, minus in place of cos square c, 1 minus sin square c, and in similar way other two brackets, minus 1 minus sin square b. After this, we can write here 1 minus sin square b minus 1 plus sin square c plus b square 1 minus sin square c. After opening the bracket, if there is a minus symbol before the bracket, the symbol inside the bracket changes. Therefore, we get minus 1 plus sin square a plus c square, again 1 minus sin square a minus 1 plus sin square b. For those whose algebra is not strong enough, I would like to give you here hint. Here suppose a square minus b square, and before the bracket there is a minus. So after opening the bracket, the symbols will change. So it becomes minus a square and plus b square. Here plus 1, minus 1 get cancelled. Here as well as here also plus 1 and minus 1 get cancelled. Now we'll write down what is left. Here is a square, here is a b square, and here is a c square. In first bracket, you can write sin square c minus sin square b, plus here in the second bracket, you can write sin square a minus sin square c plus c square. In the third bracket, sin square b minus sin square a. By sine rule, a upon sin a equals to b upon sin b equals to c upon sin c equals to k, implies sin a equals to a upon k, implies sin square a equals to a square divided by k square. Similarly, sin b equals to b upon k implies sin square b equals to b square upon k square. In similar way, sin square c equals to c square upon k square. Putting these values, then we get LHS equals to a square in place of sin square c, c square upon k square, minus in place of sin square b, b square upon k square. Similarly, in other two brackets, we get b square, a square upon k square minus c square upon k square. In the third bracket, b square upon k square minus a square upon k square multiplied by c square. Everywhere k square is there. So this can be written as a square multiplied by c square minus b square divided by k square plus b square multiplied by a square minus c square divided by k square plus c square b square minus a square divided by k square. This is equals to a square c square minus b square plus b square a square minus c square plus c square b square minus a square whole divided by k square. Now opening all the brackets, this is equals to a square c square minus a square b square plus a square b square minus b square c square plus b square c square minus a square c square. Now cancelling similar terms, a square b square get cancelled, then a square get cancelled, and even these two terms get cancelled. Therefore we get LHS equals to 0 upon k square equals to 0, that is equals to RHS. Therefore LHS equals to RHS is proved.